down, so it can't be that much work. Yeah, that's what this guy said. N plus b to the n equals c to the n. Then he went crazy, died, and actually didn't have a solution to this. What's that called? Fermat's last theorem. He wrote down in the margin like I have a proof for this, but it's too long to write down here. Mathematicians for hundreds of years tried to solve it. No one could, so they firmly believed that he either didn't have it and was lying or thought he had it and was wrong. Recently, a guy named Andrew Weil in 1997 came up with a proof. It's roughly like 300 pages long, and there's like 50 people in the world that understand it, but apparently it is correct. They're still looking for a cleaner answer. It all started, though, with that many characters. So we go over here, not quite the same thing, but in our own world, the same amount of pain.
You shouldn't have said that. It's scary.
I know, scary time. So you look at this and you're like, oh man, it's so clean. And you also want to believe it's clean because when you're looking at things with natural log or e, you're like, oh man, e to the x, the derivative of that is e to the x, so therefore there must be some sort of link and therefore it must just be done. No, no. When you looked at this, you might have realized quickly that you just don't have an easy way, straightforward way of integrating this thing. What do you could either use a table, which you're not supposed to do because you need to just know this one, or do it by hand. What method do you need to employ to integrate this thing? Some of you already said it, so I'm not like making stuff up. Come on. Parts. Parts. Who remembers covering integration by parts for at least a little while last year? Yeah, just be honest. I know you covered it. Now put your hands back down. How many people actually remember how it's used pretty clearly? Yeah, that's what I thought. Okay, so we're going to have to do story time with parts, okay? And we're going to come back to this. We're going to use it over and over and over again. This will be as second nature to you eventually as any of the other differentiation rules. Integration by parts is integration, but it revolves around starting with the product rule. So if I have two functions, sorry, go away, there we go. Hide keyboard, thank you. If I have two functions, let's say u and v, and I take the derivative of both of them, what does the product rule tell me this is going to be equal to? U prime v minus uv prime. Are you okay with that? Okay, so I've taken the derivative. If I integrate both sides now, what do I end up with? uv is equal to the integral of this thing, correct? U prime v minus uv prime. Are you with me so far? Again, please don't write this down because it's going live to your notebooks right now. If I have the integral of two things being, oh, it's plus, by the way. Don't let me do that. If I have the integral of two things being added together, what can I do with that? I can separate it. So I have uv equals the integral of u prime v plus the integral of uv prime. You with me so far? Nice. If I wanted to move things around arbitrarily in a way that doesn't seem like it's helpful, but it is, am I allowed to do this? If I wanted to? All I did was subtract the integral of uv prime. So you're like, man, now I'm just going to flip the order, and you might be like, what the heck is going on? Why would I want to do this? I'll show you why. So this right here is the statement you need to remember. You have to memorize that. The integral of u prime v is equal to uv minus the integral of uv prime. You have to remember that. That is super important. You have to. And the reason it's super important, we're going to go back up to the land of blue colored things right here. And I'll try to use a different color, right? Gray. It doesn't really come up that well, but I'll try. We're going to pick a u prime and a v. So anybody want to guess what u prime is going to be in this case? You're going to look at this and try to break it apart into two pieces. At first you might look at it and go, well, there's only one thing. There's only ln x dx. That's actually two things. What is dx going to be? Well, I just gave it to you. What's u prime going to be? Sorry. What's u prime going to be? Dx. And what's v going to be? Ln x. Now, parts revolves around choosing the right parts for the right labeling. What do you do with u prime? You need to be able to easily integrate it. Well, can we easily integrate u prime? Yeah, because what is u prime equal to dx? So what is u going to be? X. And you need to pick something for v that's easy to differentiate. Well, what's v prime going to be? 1 over x. Are you with me so far? So here's the thing. This right here, the dx, that represents our u prime. And what is the ln x going to represent? Our v. So can we apply this now? We sure can. So what does that mean this blue thing is going to be equal to? Well, what's u times v? X dx. U times v, no, x ln x, sorry, I chose the wrong one. X ln x, thank you. And then what are we subtracting? The integral of what? uv prime. What is uv prime going to be? x times what? We put the dx in because we're integrating. Well, what is x times 1 over x? 1. And what's the integral of 1? X. So we have x ln x minus x. Now, if you had looked this up in the table, that's what you're going to see. But that's where it comes from, everybody. That's where it comes from. So now you have to be careful, because what kind of integral is this? Well, you're about to see. Oh, Umi, just tell me, why is it improper?
Because the lower limit is 0 and you can't have ln of 0.
Correct. So you're doing this. So when you get to here, hey, we've integrated. We can just plug crap in. We can't, right? Because you can't do ln of 0. It's not defined. So what do you have to turn this into? You have a frowny face, so what do you turn it into? A what? Limit. Thank you. I like that. The limit as b goes to 0 from the right of x ln x minus x from b to 1. We turn it into a limit. Now, can we plug in 1? Is that okay? Yeah, sure. So let's plug these in. You get limit as b goes to 0 from the right of 1 ln 1 minus 1 minus b ln b minus b. You with me so far? Hey Matt, what's the natural log of 1? Oh, put this in parentheses, sorry. Like this, right? Yeah. Sorry. Can you, what's the natural log of 1? It's 0. So this right here, what is that? What happens to this whole thing? It goes to what? 0. So the only thing that's left right here is this negative 1. It's there. Well, this is going. What happens to this? What does that go to? 0. So what's the only thing we're really interested in at this point? Yeah, the BL and B thing. So you have to be super careful about this. Super careful. This is negative whatever B L and B. We're taking out that whole thing. So you might think to yourself, so B is going to 0. So your subconscious might be like, oh my gosh, it's a product and there's something going to 0. What's 0 times anything? 0. So this whole thing is 0. Is that necessarily true? It's not. If something's getting infinitely small, it has a superpower. It makes things infinitely small when you multiply it by things. If something is getting infinitely big, and you multiply it by things, it's superpowers, it makes things infinitely big. So if you throw a 0 and an infinity into the ring and have to multiply together, do you necessarily know automatically what's going to happen? No, you do not. So at this point, you just can't assume that this goes to 0. You have to prove that it goes to 0 or it diverges. Because the infinity could have a stronger superpower, or the 0 could have a stronger superpower. At this point, you might be stuck. Then you go back and look at the question, and it actually gives you a really good hint, which is
I can answer that question.
Which is L'Hopital's rule. Okay. Mathematicians love to cheat in legal ways. Limit as b goes to 0 from the right of ln b over 1 over b. Haha, I win. Why is the limit what? It's not negative. Oh, why is it negative? I just took that negative sign right here. That's all I did. I'm just taking pieces. Sorry. I could drop that and it's fine too. Ready? Go away. Okay. Is this the same as this? Yeah, it is. But here's the thing. What happens as I'm very pleased. I'm the one that invented this. As b goes to 0 from the right, what happens to this? As it goes to 0, what does this go to? It's big, right? 1 over something small. 1 over something small. This goes to infinity. What does the top go to? Yeah, negative infinity, but it doesn't matter. It is an indeterminate form. It can be positive and negative, right? So this goes to infinity, negative infinity. This goes to, is this an indeterminate form? Yes. So what does that mean we can apply? L'Hopital's rule. So this way, you know what? I'm just going to do this. Get rid of the negative. That's what the h means. So you take the derivative of the top. What is the derivative of ln b? It's 1 over b, correct? What's the derivative? And remember, this is b to the negative 1 down here. What's the derivative of b to the negative 1? And we can just simplify this to be b to the what? Negative 1. Does this simplify? Limit as b goes to 0 from the right. Negative what? B. What does that equal? Wait for it. What's that equal? 0. Thank you for your confidence, kids. It's 0. We've gotten it to the point where it is 0. So, what have we now shown? This goes to 0. So what does this whole thing go to? -1. Now we're done. So what am I going to graph right here? This right here is ln x. Do you agree? What happens to the function as you go to 0 from the right? It goes down to -infinity. As you go to 0 from the right, this goes down to -infinity. So this goes to -infinity, this goes to +infinity, so it's indeterminate.
This will be 1 over as it gets closer to 0, right?
1 over it gets to 0, so this right here goes to 0. This goes to +infinity, this goes to -infinity. It is an indeterminate form, so that means you can do this. You have to have 0, you have to have 0, 0, or infinity, infinity. Then you can use L'Hopital. Can you use L'Hopital multiple times? Do you need to in this case? No, you actually can't, because once you do this, is this an indeterminate form? No, this is like, oh my gosh, just plug in 0 and you're done. On a limit, what's the first thing you always do? You always check to see if you can plug in the target. I can guarantee I'm going to give you something that looks terrible sometime in the future, and you're going to be like, man, I'm going to do like L'Hopital do like 6 times and integrate the parts, and then you're going to end and cry a little bit because you realize you can just plug in like 7 no. Okay? Okay, someone pick one more that we need. Alright, it's a good time. Hey, did this thing just lose again? For some reason it's being real quirky with my configuration right here. Yep, okay. We have 0 to 4, man, I picked some good ones. Over u squared minus 16. When you looked at this, what's the first thing you noticed structurally? What's the first thing you noticed? Okay. You can factor the denominator, thank you. So you could write this as 0 to 4, or put the negative outside, 1 over u plus 4 times what? U minus 4 du. Right? Are we okay with factoring? We okay with this? At this point, you need to remember what to do with this thing right here. Does anybody know what you have to do with this thing? You have to break it apart into 2 pieces. One of them will have A on top and one of them will have B on top. How do you figure out what A and B are?
But when you like multiply it by the it's like u minus 4.
1 equals A to, yeah, exactly. Plus B times what?
U plus 4.
Yeah, we've just gotten rid of the denominator, right? So this has to be true for all values. This has to be true for, so we can multiply this out if we want to. We got 1 is equal to what? AU minus what?
I'm just so confused about how
Yeah.
Okay, ready? This is called working with fractions, everybody. What's the common denominator? You know this. Don't sell yourself short. What's the common denominator? U plus 4 times U minus 4 is the least common denominator, right? You multiply everything by U plus 4 times U minus 4, and what do you end up with? A times U minus 4 plus B times U plus 4. Are you with me so far? Got it? Yay. So at this point, you need to figure out what values of A and B make this true. Anybody have an idea about how to do that? Do the distribution. 1 equals A times U minus 4 times what? A plus B times U plus 4 times what? B. So let's group together a few of these things. So that's AU plus BU minus 4A plus 4B, like this. Do you agree with that? This right here, what do you know this has to equal? 1 has to equal negative 4A plus 4B. Do you see why? Are there any U's on this side? So what's the only way you get to number 1? With these pieces right here. You with me? What does AU plus, oh, look at this. Are there any U's on the left? Are there any U's on the left? So what do you know A plus B has to be? You know A plus B. Look, are there any U's on this side? No. So A plus B has to be what? I don't understand that much. Okay. Try again. Trying again. I'm trying again. I'm trying again. Ready? I'll do it again. 1 is equal to a plus b times u minus, let's do it this way, plus 4b minus 4a. So 1 is equal to a plus b times u plus 4 times b minus a. A and b are numbers. U is a variable. You with me so far? Are there any u's on the left side? No. There's 0 u's on this side, right? So this piece, for these two things to be equal, this piece has to be the same as this piece, right? That's the only place the u's come from. Are you with me? So a plus b has to be what? 0. How many u's do I have on the left side? 0. How many u's do I have on the right side? A plus b of them. For these two things to be equal, 0 must equal a plus b. 1 must equal what? This whole thing. For these two things to be equal, 0u has to be equal to a plus b times u, and this right here tells us what has to be true. 1 has to equal 4 times b minus a. What can you divide both sides with right there? What can you divide both sides by? Oh wait, you don't need, you can divide both sides by u. Doesn't really matter, but you end up with 0 has to be a plus b, and this has to be true, both of them. You have two equations and two variables, so what can you now solve for? What's it equal? What? Negative 1/8. But we know a plus b is 0, so what does b equal? 1/8. So did we just get a and b? We did. So now we go all the way back up here. What did we say a equals? 1/8. So what does b equal? Why did we do all of that work? What can we now do? Oh, did I flip it? I flipped it. Sorry. Thank you. So a is negative 1/8 and this is positive. Sorry. So now what's the whole point? Yeah? We don't need to use u substitution, but the bigger point is we've broken it apart into two fractions. Each of those fractions can be integrated. We've now taken something that's bigger that we couldn't integrate, and we've broken it into two pieces that can be pretty easily integrated. So what do we have here? We now know that this equals negative 0 to 4 of negative 1/8 over u plus 4 du plus the same thing, but what do we put on the inside? 1/8 over what? U minus 4 du. I'm not going to do these out, but these individually, can you integrate both of these? Yeah, you drop these 8s, you pull it out to the outside, make it 1/8, right? What's the integral of this? You can finish this now. What you've now done, apparently, partial fraction decomposition. You can look it up. Everybody stand up. Whether or not things converge. So there are some other tests that we need to talk about. So here's the first one, which is really cool. And what's nice about these tests is not that really, these tests, we don't have to prove why they work, we just get to use them, which is great. Here's what's really cool. If the absolute value of each individual element of a series, if you take that new series, if this converges, then so does the original series, without the absolute value. So for example, look at this alternating series right here. 1 minus a 4th plus a 9th, it would be minus a 16th plus a 1/25th. It's alternating, who knows, right? Take the absolute value of all the terms, and what do you get? 1, 1/4, 1/9, 1/16, 1/25. That's 1 over n squared, right? What do we know about the series 1 over n squared? It what? It converges because it's a p series with p greater than 1, right? So because the absolute value of the series, each element converges, because the absolute value converges, this must converge. This is really important for you to realize, the most important thing about this. This is monodirectional. If this converges, then so does this. If this converges, does the absolute value have to converge? No, it doesn't. So it's really important. It's only this direction. If the absolute value of a in series converges, then so does this, but not necessarily the other way. That's really the only thing you need to remember to be careful of. Be very careful. Umi's probably quizzically frowning a little bit because she would like an example of when that's true, and I will give you one later, okay? I will give you one later, but to give you an example, we need one of the other tests first, okay? I think the most joy and drive you to the most frustration at times. Ratio test is really cool. Geometric series, do we have a way of really easily telling if a geometric series is convergent? Yeah, if the ratio is less than 1, it converges. If it's 1 or greater, it diverges, right? There are series that start behaving like geometric series eventually. So this is what you get to do. Let's say you have a series. You look at the ratio of a term in the next term, the general term in the next term, and you look to see if it has a limit L. You do this limit. It's always going to have a limit. It might be infinity, it might be 7, it might be 1, it might be a half. Okay? But you do the limit of the ratio. The limit of the ratio. So here are the terms. They're doing something, right? You're seeing what is the limit of the ratio of successive terms. And here's what's really cool about it. If L is less than 1, then it converges. Which is kind of like a geometric series, right? If eventually this series starts looking like a geometric series with a ratio less than 1, guess what? It converges. If it's greater than 1, or if L is infinite, then it diverges, right? If the series is blowing up individually, then what happens if you add them all together? It really blows up. Here's the line that's really going to piss you off. You're going to do some crazy algebra, be very proud of everything, and be like, awesome! It comes down to 1. If L equals 1, then the test does not tell us anything.
What?
So when you use the ratio test, you're really looking for it to blow up or go to like a half. If it goes to 1, you're like, damn it. Come on. What the heck? Dang it. So let's use it once, okay? Let's use it once. So this thing right here, this series. It's fun, okay? So in this case, an is given to you. What is an? 1 over n factorial. What is an plus 1? 1 over what? N plus 1 factorial. If you have an, if you have the expression for an, how do you go to an plus 1? You just replace n with n plus 1. That's all you do. Could there be multiple n's all over the place? Sure. Could you have some crazy thing right here? Yes, you will. You'll see nasty things. And then what's the next term? You just increment it by what? 1. So the ratio test says you do the limit as n goes to infinity of the next term over the current term. And you see what happens. When you divide by a fraction, that's the same thing as multiplying by the reciprocal. So what are you going to end up with? N factorial over what? So then you have factorials, which you guys love, right? Can someone tell me what this simplifies to? Anybody? Well, let's do it out. Hold on. We have the time, so I'm going to write it out for you. What does n factorial mean? N times n minus 1 times n minus 2, right? What about this one? This is n plus 1 times n minus 1 times n minus 2, right? Correct? What happens? So what are you left with? The limit as n goes to infinity of what? 1 over? What does that equal? 0. So then we go back and look at our list. If it's 0, what does that mean? Converges. It should kind of make sense in the terms of this one because you know of things that are a lot bigger than these that converges. So like 2 factorial, do these numbers get really big really fast? Yeah. 3 factorial is 6, and then you get 24, right? It's pretty big, right? Well, we know that like the 1 over n squared converges, right? These terms are a lot smaller than the 1 over n squared terms, so it should kind of make sense. But this one's pretty cool. It cancels out, it goes to 0, you're done. What's the frustrating number to see? 1, no less than 1. Dang it, why did I do that? It doesn't tell me anything. Yes?
So if we get one, what should we do?
Look for another really fun. So an alternating series is something that goes positive, negative, positive, negative, positive. Good start there, but an alternate sign. Here's something that's really cool about alternating series that we have to prove we get to use it. You ready? This converges if you see how it's an. What does this do? The negative 1 to the n minus 1. What does that do? It just flips the sign over and over again, right? So if an right here, if an plus 1 is always less than, so this thing is decreasing, the non-sign part of the piece, if it's decreasing for all n, and it goes to 0, guess what it does? It converges. So if you have, I gotta move this over, sorry. If I can move it over, yeah. Alternating series converge if the terms get smaller and they go to 0. This is really cool. So for example, you ready, Omi? By this, what is this right here? That's the something harmonic series. No. What does the negative 1 to the n minus 1 do? N is going, when n is 1, what is that? N minus 0, negative 0. So it's going to be, what does this equal? 1, then what? 1 over 1, then what? Minus 1 over 2, right? Plus 1 over 3, minus 1 over 4, plus 1 over 5. This is called the alternating harmonic series. But look at what we have up here, Umi. This alternating series test says that if a series is alternating and it's going to 0 and each term is getting, the absolute value of each term is getting smaller. So is the absolute value of each term getting smaller? Yes. Is it going to 0? Yes. So therefore, what does this do? Therefore, this converges, right? But does the harmonic series converge? No. We're not proving this. We're not proving it, but you wanted an example, okay? And this example totally relies on this. So here's the thing. In this case, we know that the absolute value of this does not converge, but it itself converges. So remember the first thing we saw here, I said it's monodirectional, and you were like, but wait, how is that possible, right? In this case, we know that the alternating harmonic series converges, but if you take the absolute value of it, it becomes the harmonic series, which does not converge. The picture that they give in the book. So you want to know like why that's true? So let's look at these pieces for a second. Where is it? Right here. See these pieces right here? If you have an alternating harmonic series, let's think of it like this, 0. So this first one was at what, 1, right? Let me use some colors here. It goes all the way to 1, but then it takes away what? It takes away a half. You'll see pictures where it'll go a half this way, and then it'll go, and then it goes a third this way, and then it goes a little bit less, and a little bit less. You'll see these pictures that have to do with like the overlap of the colors, and it helps you believe that this converges. Because it's alternating, it helps obliterate the behavior on both sides and creates something that definitely converges. You don't have to prove this. The page you'd want, I want to do one of these with you, just so you can remember. Factorials, you have to be very, very, very careful with, okay? Be very careful. So let's do 14. It says use the ratio test to determine whether or not it converges or diverges. They give you, this right here is an. So what limit are we looking at? The limit, yeah, that's right. The limit as n goes to infinity. What's the next term going to be? 1 over what? 2 times n plus 1 all what? And then what's the an term? 1 over 2n factorial. Do you see how super careful I was with those parentheses? Do you see that? Real careful, right? Because if it's 2n in parentheses factorial, you have to replace the n with n plus 1. Dividing by a fraction is the same thing as multiplying by the reciprocal. So now we have the limit as n goes to infinity of 2n factorial over what? 2 times n plus 1 factorial. And at this point, you have to be super careful with simplification. What does factorial mean? You take the number, then you subtract 1 and multiply it, subtract another 1 and multiply it, subtract another 1 and multiply it. You with me so far? So the top is not that bad. This is the limit as n goes to infinity. What's the biggest number? 2n. What's the next one? 2n what? Minus 1 times what? And so forth, right? Before you do the bottom one, please distribute what's inside the brackets. What do you get inside the brackets here? 2n plus what? So this is the same thing as 2n plus 2 factorial. So you do 2n plus 2. What's the next one down? 2n plus 1. And then what? 2n, and then 2n minus 1. And then what are you hoping always is going to happen? Gone, 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 gone. They all go away, right? So this is equal to the limit as n goes to infinity of what? 1 over what? Plus 2 times. And what does this definitely go to? What does that definitely go to? 0. So because that goes to 0, what have we shown about this one? Converges. You will do similar work for 15. But you have to be super careful about the squares and the factorials. Yes? 15 doesn't look much different than 14, right? I gave you something. Here's the work for 15. The squaring blows things up a lot, okay? You just have to be really careful, okay? Don't be lazy at any point, but especially when you're dealing with factorials and squares. Okay, so we're